Good evening, everybody. It's currently 9:30 on February 6th. I'm recording this video. We're looking at Module 9, 10, and 11. To balance out the quite short video we had for Module 8, this one will be just a tad bit longer, as we need to work through kind of 3 modules here. And these 3 modules are really going to talk about basically our atmosphere, how it's structured, why there's wind, where that comes from, and then how that wind kind of influences the ocean and the ocean currents. And so in the first module, we're looking at the unequal heating of Earth. We're going to identify the 5 layers of the atmosphere, discuss the factors that cause the unequal heating of Earth, and describe how the tilt affects the season. Our Earth's atmosphere, our first 2 layers are the troposphere, layer of the atmosphere closest to the surface of the Earth, and the stratosphere. 2 things that you want to note about both of these is that the troposphere is where all weather occurs, and the stratosphere is where our ozone layer is, which is very important because the ozone layer is what is blocking all those harmful UV rays, which can cause DNA damage to humans. If you look at the Earth's atmosphere as kind of a graph of temperature and altitude, you can kind of see for the most part the trend is as we kind of increase in altitude, we are decreasing in temperature. Really the thing you want to note here as you're kind of identifying the different levels of Earth's atmosphere is 1, you should know the order of Earth's atmospheres. And 2, you should be able to identify kind of the temperature trends within each level. So you should know for the troposphere that basically as altitude decreases, the temperature decreases. In the stratosphere, we actually get a little bit of an increase in temperature. The mesosphere, we get a decrease. And then the thermosphere, as we climb higher and higher out of the atmosphere and more towards space, our temperature is increasing. And then another thing to note too, the thermosphere, this is just kind of a cool extra thing, that is where the aurora borealis sits, because the thermosphere has a bunch of charged particles in it, and if you're ever lucky enough to go to Alaska or Iceland or anywhere, it has to be closer to the poles to see the aurora borealis. It is very beautiful. The amount of solar energy reaching Earth varies with location. As the sun's energy passes through the atmosphere and hits land and water, it warms the surface unevenly. And this happens because of a couple of things. 1, the angle at which the sun's rays strikes varies. So unlike some people think the Earth is not flat. So if the Earth was flat, we would get an even level of heating, but we are not Kyrie Irving, so the Earth is a circle, and this means that we get an uneven and different angles at which the sun's rays strikes. The amount of surface area over which the sun's rays gets varied as you go from different latitudes, and some areas of the Earth reflect more energy than others, and this is something called albedo, which we'll talk about in a minute. So as we're looking at why different areas of the Earth get heated more, if you look at the equator, where for the most part the sunlight might strike the Earth at a perpendicular angle, you're going to get lots of sun energy hitting a very small area. Whereas if you go more up towards the poles, because the Earth is tilted, the sunlight will strike the Earth at an odd angle and it will spread out its energy over a larger area. So you can imagine that a more concentrated energy spot, the temperature will get more energy, it will be a little bit warmer, and then if the energy is more spread out, you're getting a little bit cooler in those areas, different amounts of energy. Also, the thing that changes whether the amount of solar energy reaching Earth is high or low is something called albedo, which basically the amount a surface can reflect energy. So this is really like dark and light. So if you think about going outside on a summer day and you wore like a black long sleeve t-shirt, you're going to be really hot. Your black shirt is going to absorb a lot of the sun's energy. It's what we could say has a low albedo. Whereas if you were going outside, you'd be smarter. You'd say, oh, I'm going to wear a white shirt today because it's super hot. Your white shirt's going to be very reflective. It's going to reflect that light. So think about also when you step on like pavement, like blacktop in the summer, super hot, right? It's absorbing that sun's light. Or even like fresh snow. You go outside and it's blinding outside. You can't see because why? Because that sun is reflecting off that white snow so much that it's very light outside. So here's just some different examples of different albedos. Water can range depending on the angle, but usually it can be a little darker, so it's going to absorb more. Sea ice is usually a little higher. Blacktop is lower. Fresh snow, like I just said, very high. So really, when we talk about high albedo, we're talking about high reflectivity. So we measure albedo from 0 to 1. 1 means that we are 100% reflecting the energy, 0% absorbed. There's really nothing that can do that on Earth. And then low albedo is 0, so 0% of the energy reflected, 100% is absorbed. And then the most important thing here is that the Earth's tilt causes seasonal changes in the climate. The Earth's axis of rotation is tilted at 23.5 degrees. And when the northern hemisphere is tilted toward the sun, the southern hemisphere is tilted away. And this is what causes our seasons. So, excuse me. So as we look at kind of this diagram here, we notice that as the northern hemisphere, as it's the Earth is circling around the sun and the northern hemisphere is tilted towards the sun, this is when we have summer in June and July and August. And as we rotate around and now we are tilted away from the sun, this is when we have winter and the southern hemisphere has summer. So the Earth's seasons have everything to do with the tilt and really nothing else. It all has to do with that tilt for the Earth's seasons. Okay, Module 10. This is about air currents. So talking about why there is wind. So explaining the properties of air and how it moves in the atmosphere, identifying the factors that drive atmospheric convection currents, describing Earth's rotation and how that affects air currents, and how air currents move over mountain ranges. So air has several important properties, and these are some things that you should know and we'll kind of talk about as we go through here. The saturation point is the maximum amount of water vapor in the air at a given temperature. We have something called adiabatic cooling, which is the cooling effect that as air rises in the atmosphere and expands, it cools. Adiabatic heating is the heating effect of increased pressure on air as it sinks back towards the Earth's surface. And latent heat release is the release of energy when water vapor condenses into liquid. So basically when water goes from gas into a liquid, it releases heat, and that's what's called the latent heat release. All right, so all of this plays into what's called atmospheric convection currents. Now, this word convection is going to come up quite a bit here. There can be convection currents in the air, in the water, and then also when we talk about tectonics and stuff moving underground as well. But it's basically an atmospheric convection current is the global patterns of air movement that are initiated by the unequal heating of Earth. So, in basics, we have some areas of the Earth that the surface heats up, and that dry air, as it's moving along the surface, will pick up water and it will heat up. That air, hot air, rises, okay? And so it's rising up, it's rising up and rising up, and as it rises up, it cools. And at some point, it cools to the point where that hot air starts to condense, and that's how we get clouds and rain. So it'll rain, and then as the rain and the air is releasing the water that it was holding, it cools and it's now dry because it no longer has any of that humidity in it, and so it dries and the cold air kind of sinks back to Earth where it rewarms again. And so this is a convection current where hot air picking up moisture rises, it hits its saturation point and condenses, which forms clouds and rain. It releases a bunch of heat through latent heat, and then as it continues to climb, it cools up in the atmosphere, and since it's now cold, the cold air wants to sink back down. To kind of give an example of this, and this is something that we will do in class 2, if we look at this video here, basically within the video here we have kind of a hot cup of water underneath this tub that is heating just this red food coloring, and then we have this blue food coloring along the side. And so as we kind of watch here, we can see that the hot food coloring is being heated, and that heat is rising. And as that is rising, we have this cooler water that's over here that's not heated coming in to replace it. And then you can kind of see that as that cooler water hits this hot spot, it is also, kind of back up a little bit. we could see that as this cooler water comes in and it hits this hot spot, then it's getting heated and it's rising. Okay? And so we have this is a convection current. Hot air is rising, and then it gets displaced over here. It cools, comes down, hits the hot again, and rises back up. So where does this happen? We actually have three kind of different places in the northern hemisphere and the southern hemisphere where this happens. And we call these different cells. So we have what's called the Hadley cell, which is a convection current in the atmosphere that cycles between the equator and 30 degrees north and 30 degrees south. We have something called the ITCZ, which is the latitude that receives the most intense sunlight. This is usually near the equator, and this is where two Hadley cells converge. And we'll show you a picture of this later. We have a polar cell, which is a convection current that is kind of at the poles, so 90 degrees north and 90 degrees south down to 60. And we have a Ferrel cell, which sits in between, a convection current that sits between 30 and 60. So if we see a diagram here of the Earth, we have rising, warm air rising and cool air falling kind of in 6 different parts. So we have our Hadley cells, which are closest from the equator to 30 degrees. So you have warm air that is the warmest air sitting near the equator. That warm air will rise, and as it rises, then it eventually cools, it falls, and then it gets heated again, rises, cools, falls, rises, right? And so it keeps going like this. We have another kind of convection that happens here and another one that happens at the top. So we just call the 60 to 90 degree one a polar cell, the 30 to 60 degree one a Ferrel cell, and the equator to 30 degrees a Hadley cell. And then it just repeats on the northern hemisphere as well. And then here's that ITZZ, which is usually the equator, but can kind of adjust a little bit, which is the most heat that the Earth receives. And so what I want to show you here is a kind of simulation here of a video I found where they kind of talk through these currents and why they kind of rise and form, and it's got some good animation. So I'm going to let him kind of explain and just kind of play the video. It might kind of sound a little weird at first, but then it should be okay. I'm just going to play this video and kind of watch this to help kind of explain these cells, convection currents, these air currents even more.
Look at global wind patterns and talk about the reasons why the air circulates the way it does, and also patterns of rising and sinking air and how that relates to precipitation. The engine that drives it all, I guess you could say, is the intense heating by the sun that occurs in the equator areas where the sun is shining at a very high angle of incidence. And this hot air near the equator, being less dense, rises upward. It rises upward and it moves toward the poles, and then it gradually sinks at about 30 degrees north and south latitude. So we create these big spinning circles of air that we call the Hadley cells. Now, near the equator where the air is rising, it loses its ability to hold moisture, and you get a band of high rainfall and low pressure because there's air leaving the equator. Where the air sinks, in these belts at around 30 degrees north and south, you get high pressure sinking air, which creates areas of clear skies and desert climates. Now, as this air circulates and tries to flow back toward the equator along the surface of the Earth, or as some of it heads toward the North Pole or toward the South Pole, the Coriolis effect, the spin of the Earth, causes it to bend and turn, and it's going to create the two big wind belts that prevail on our Earth, 2 out of 3, the trade winds, northeast trade winds and southeast trade winds, and then the prevailing westerlies. Now these winds curve, and the way they do because of the Coriolis effect. The winds curve to the right of their path, north of the equator. They curve to the left of their path, south of the equator, and they end up flowing from east to west or from west to east. Now the other big factor is what's happening at the poles. At the poles, the air is cold, and the cold air wants to sink. And as that cold polar air sinks, it heads toward the equator, and it bumps into this air heading toward the pole here and toward the South Pole here. And it creates an area of rising air, and again, rising air produces high precipitation belts at about 60 degrees north and about 60 degrees south latitude. At the poles themselves, the precipitation is quite modest because the air is sinking, and that creates low precipitation.
Okay, so that just gave a pretty good animation there, kind of looking at the currents in total. Now he started to talk a little bit about those wind patterns, and so we'll kind of jump into looking at some of those wind patterns a little bit here. Um, so he just kind of went over those convection currents, but again, just to review a little bit, here we are at the equator, at the ITCZ, which is the spot where the sun kind of heats the most on Earth. We have hot, we actually have where the two Hadley cells kind of combine. We have hot air rising, and we get a lot of rainfall here at the ITCZ, and then this dry, cold air after it has kind of released all of its water and it's released all of its heat. It's now drying and cold, and that cold air wants to sink back down, and we go again and again and again. And one of the coolest things that I always thought was that at this point, if you wanted to identify where a desert is, since a Hadley cell is from the equator to 30 degrees, if you notice, right here in the middle is where we get all of our rainfall. Well, what do you know? If we look right along the equator, obviously that's where we find all our rainforests. That's where the two Hadley cells converge. That's where the most heat is striking the earth, so there we have the hottest, moistest air that is being lifted up and dropping all of its rain. Well, once it does that and it drops all of its rain, now we have very, very dry air that's settling back down at the 30-degree north and 30-degree south mark. So if we look at that latitude across the world, what do we find? That's where we find all of our major deserts. So if we trace right along the 30-degree mark, give or take, we can find a lot of our major deserts. I always thought that was kind of cool. And then he talked about the Coriolis effect. So this is something that we'll do in class because it's kind of a hard thing to wrap your head around as to kind of why those winds kind of curve a little bit. And so I'll try to explain it very quickly here, and then in class we'll do something that I think will make it a lot easier to understand. But basically the Earth rotates, and because the Earth rotates, there's actually the equator and the North Pole will actually rotate at different speeds. I know it's kind of crazy to think about. This kind of causes a deflection to happen to the wind that's kind of rotating around. So the Coriolis effect is what's basically is the deflection of an object's path due to the rotation of the Earth. And so our winds, our major wind patterns, go a certain way because of the convection currents, but also because of this deflection of the Coriolis effect. So essentially what's happening is that when we are in the northern hemisphere, we will have, because of the Earth's rotation, we have deflections of wind patterns that go to the right of their path. So this is going, I know this looks like it's going left, but if it's already going this way to the right of its path, okay, so its path is going this way to the right of its path. Path is going this way to the right of its path. And in the southern hemisphere, things get deflected to the left. So here's its path, left of the path. Here's its path, left of the path. And so that's what's called the Coriolis effect. So if we look at the major wind patterns that are created by these convection currents, we have the northeast trade winds, which start out coming this way and then get deflected to their right. We have the westerlies, which start out coming this way and then get deflected to their right. We have the southeast trade winds, which start this way and get deflected to their left, and the westerlies of the southern hemisphere, which start this way and get deflected to their left. So because of the Coriolis effect, because the Earth rotates at different speeds depending on whether you're at the equator or the North Pole, it actually deflects the wind patterns. And in the northern hemisphere, it's deflecting to its right, and then in the southern hemisphere, it's deflecting to its left. And again, we'll do a little demonstration in class that I think will make this a lot easier to understand. And then the last thing about air currents is what's called a rain shadow. So this is basically where mountains, if you have a pretty large mountain range, you can cause one side of a mountain range to be very humid and rainy and the other side of the mountain range to be very dry. So basically what happens here, I'll use the example of Hawaii here in a second, is that you have very warm, moist air that is coming across this land. Because of the mountain range, it's kind of gradually elevating that air up in altitude. And as we know from the convection currents from earlier, as warm air rises, it starts to condense and form clouds and rain. So on one side of the mountain, you have very rainy parts, and then as that air loses all of its moisture and starts to cool down and goes over the other side of the mountain, now we have a very dry and a desert region on the other side. And kind of an example I like to think about, because I've been there before, and it's kind of an easy way for me to remember, is that on the big island of Hawaii, the wind patterns are coming this way, so from right to left. And the city of Hilo is incredibly rainy. If you look at its forecast, I mean, you have rain projected almost every single day because you have this warm, moist air from the ocean coming this way. You have the volcano, which is basically this incredible mountain range that's splitting the island in half. And so, as this warm air basically rises up against the side of the mountain, it's dropping all of its moisture as it cools and condenses and clouds up and drops everything. And then as the air makes its way over the mountain, it's now dry because it's lost all of its rain. And now the other side is warm and almost never rains. So pro tip, if you are looking to stay in Hawaii, you want to stay on the left side of the island because you're looking at mostly sunny weather with very little chance of rain. If you stay in the Hilo side, you're looking at rain almost every single day. I'll leave this up here, but it's basically everything that I just said. Okay, Module 11, ocean currents. We're not going to go through all Module 11 because we'll do a little demo of El Nino in the classroom, but the same convection currents that we saw in wind happen in water too, as we have warm waters and cold waters that mix with each other. And then the wind patterns that we just talked about also influence the ocean circulations as well. So surface ocean currents move warm and cold water around the globe. Ocean currents are driven by a lot of things. It's a combination of temperature, gravity, the prevailing winds. So again, the prevailing winds, remember, are things like trade winds and the westerlies. The Coriolis effect, which remember is like that deflecting because of the Earth's rotation, and where the continents are. Warm water, like warm air, also expands and rises. And then there are things called gyres, which are basically large-scale patterns of water circulation. And again, they differ in the northern versus southern hemisphere. So in the northern hemisphere, these gyres or water circulations move clockwise, and in the southern hemisphere, they move counterclockwise. And so here's kind of a map of the ocean currents, or the major gyres. And so you'll kind of see here that we have warm water, or sorry, not warm water, but we have a clockwise kind of rotation of currents here, and we have a counterclockwise rotation of currents here. And again, why are the currents moving this way? It's because of all those things, from the Coriolis effect to gravity to wind patterns, and all kinds of things put together. Oh, I lost my, oh, there we go. Lost my internet. Good job, Time Warner. Okay. And so one of the huge things that's probably the most important about all of ocean currents is what's called upwelling, which is basically where the cool waters end up coming up and displacing warm water. It's the upward movement of ocean water to the surface that basically brings a bunch of nutrients up to the surface that supports large populations of producers, which in turn support large populations of fish. And so that is hugely important, and is the reason why many populations of fish along the coast, especially in coral reefs and stuff like that, can prosper so much, is because of this idea of upwelling, which we will again do a little simulation in class because it's hard to talk about here. It's easier to do little demos in class. But I'll try to show something here that'll hopefully help you with it. Deep water currents circulate ocean water over long periods of time. So not only just these gyres, but also there's a deep water current that kind of circulates the ocean, and this is called the thermohaline circulation. It's an oceanic circulation pattern that drives the mixing of surface water and deep water. Scientists believe this process is crucial for moving heat and nutrients around the globe. And it appears to be driven by surface waters that contain unusually large amounts of salt. And so basically here is the thermohaline circulation. So basically the gist is that we have warm waters from the Gulf of Mexico flow to the North Atlantic, where some of it freezes and evaporates. Since some of it froze or evaporates, since salt doesn't freeze and salt doesn't evaporate, that means there's more salt left over in the liquid water. This kind of makes that water now saltier. Saltier water is denser, so that means it's going to sink. And so we have these surface waters that now have lots more salt and they sink, and that creates very cold, deep kind of flow of water that then makes its way back across the globe. And so you can imagine how important that is for kind of moving nutrients and circulating water around the globe. And to kind of give you a little bit of a simulation of that, here's kind of a video where you can imagine this guy is putting a huge block of ice. So we can imagine this is like the Arctic. So we have warm waters moving in to the Arctic. And this guy's going to put some food coloring in right next to it. So we can imagine the food coloring is like the warm waters that just came up to the Arctic from the Gulf of Mexico. So if we're looking at our picture here, it's these warm waters. We just got up here, so here's the big ice block. And now what's going to happen? Some of that water is going to freeze, and the water is going to become saltier. And so what's that water going to do as it becomes saltier? So that water is the blue food coloring. As the water now becomes saltier, it's going to become denser, and that's going to cause the water to sink. And so it's going to sink down, and this is the start of that cold, deep current that then makes its way back all across the rest of the ocean. And so if we look at kind of an animation here, that will kind of show the same thing. Let me pause this so it doesn't go anywhere. Okay, so here's those very warm waters from the area around the Gulf of Mexico. They get brought up, okay, here into Greenland and Iceland, and as some of it gets frozen or some of it has evaporated, that water's become saltier and it sinks. And now that water sinks and it kind of goes into a deep current, which then starts to make its way back, starts to make its way back, and it's kind of rotating and circulating all the way back down, bringing a bunch of these nutrients. So we have these surface, the lighter colored ones are kind of the surface currents, and then we also have this very deep current that's going on as well. And with all that stuff happening on, that's kind of how all the nutrients get circled around the globe. And so that's what's called the thermohaline circulation. Because of that very salty water is denser, it creates a very cold current that circulates everything back around. And again, I just kind of talked about that there, but I'll leave that there. So we'll do a bunch of demos and stuff like that in class that I'm hoping will kind of help make that stuff easier. I know it was a pretty long video, but it was a lot of dense stuff that we had to kind of get through. So hopefully you have a wonderful day or evening. Adios.